Now we meet the hero of this whole film, a number that turns out to be a price in disguise. Let's earn it with the simplest problem I can think of. No curves yet, just two ordinary numbers, x1 and x2. Of all the points on the line x1 plus x2 equals 5, which one sits closest to the origin? Let's turn that picture into math carefully, because this translation is the whole game. Closest to the origin means the distance to the origin is as small as possible, and that distance is the square root of x1 squared plus x2 squared, straight from Pythagoras. Now here's a small lovely trick. The square root doesn't change where the minimum is. The closest point is the same point whether you minimize the distance or the distance squared. So drop the root and just minimize x1 squared plus x2 squared. There's our objective. And on the line, that's the leash. The point must obey x1 plus x2 equals 5. That's our constraint. So the geometry has become one clean statement. Minimize x1 squared plus x2 squared subject to x1 plus x2 equals 5. That is constrained optimization. And to crack it, we'll use a method that carries all the way to optimal control, Lagrange multipliers. Here's the move. Build one new function, the augmented function, fa. Take what you're minimizing, x1 squared plus x2 squared, and add a brand new variable p times the constraint written as equals 0, x1 plus x2 minus 5. So fa equals x1 squared plus x2 squared plus p times the quantity x1 plus x2 minus 5. That new variable p is the Lagrange multiplier. Now the magic. Pretend x1, x2 and p are all free, independent knobs, and set every partial derivative to 0. Count them, 3 knobs, so 3 equations. The partial with respect to x1 is 2x1 plus p equals 0. With respect to x2, 2x2 plus p equals 0. And with respect to p, this one just hands back the constraint, x1 plus x2 minus 5 equals 0. 3 equations, 3 unknowns. The system is closed, so we can solve it. The first two equations say x1 and x2 both equal minus p over 2. Put that into the constraint and you get p equals minus 5. So x1 and x2 are each 2.5. There's the closest point and a multiplier of minus 5. And that minus 5 is about to mean something very real. That wasn't a one-off trick, it's the general recipe. You just watched 3 equations close around 3 unknowns. Write it in general to extremize a function of n plus m variables under n constraints. Form fa, your function, plus a multiplier pi times each constraint, and set the partial with respect to every variable and every multiplier to 0. The bookkeeping always balances. 2n plus m equations in 2n plus m unknowns. In our warm-up, n was 1 and m was 1. So 2n plus m is 3, exactly the 3 we just solved. Now why should a trader care? Because of what that multiplier means. The number p is a shadow price. It tells you how much your best possible cost changes if you loosen the constraint by 1 unit. Make it concrete. Our best cost was 12.5 at budget 5. Now relax the line a little, letting x1 plus x2 be slightly more than 5. The best cost rises at a rate of 5 per unit of slack, and that 5 is exactly the size of our multiplier p. The multiplier is the price of the constraint. In market making, that shadow price is the co-state. The famous Avellaneda-Stoichkov's Q, gamma, times inventory Q times volatility sigma squared times the time left, big T minus T, is exactly this. The marginal cost of carrying one more unit of inventory. Not bookkeeping, the price of risk. Now lift the idea from points to whole paths. We want to minimize a functional j of a vector function w. But W is chained by a constraint that must hold at every instant. F of W and T equals 0. A point constraint, like forcing the path to live on a surface, a bead on a bent wire. The move is the same, just promoted to functions. Let the multiplier become a function of time, P of t, so it can enforce the constraint moment by moment. Form the augmented functional, the integral of g plus p transpose times f, and define the augmented integrand g minus a as g plus p transpose f. Then the condition is beautifully familiar. It is just the Euler equation, written for g minus a instead of g. The partial of g minus a with respect to w minus the time derivative of the partial with respect to w dot equals 0, plus the constraint itself. You fold the constraint into a new integrand and turn the very same crank. This is the peak everything has been climbing toward. Now let the constraint involve the rate of change, f of w, w dot and t equals 0. A differential equation constraint. And here's why that changes everything. Split the vector w into two stacked pieces, the state x on top, the control u below. A constraint that ties the rate of the state to the control is just a system's equations of motion. The state isn't free, it's driven by the control you choose. The method doesn't blink. Form the same augmented integrand, g min a equals g plus p transpose f. Write the same Euler equation on g min a. Add the constraint back. Done. But look at the structure that falls out. Some of these equations are differential. They involve rates, they describe things evolving in time. And some are purely algebraic, no derivatives, solved instant by instant. Precisely m of them, the ones for the control, are algebraic. The other two, n, for the state and the multiplier, are differential. Why exactly that split? That is worth seeing for ourselves. Let's see exactly why some conditions are algebraic and some are differential on the smallest system there is. One state x, one control u with dynamics x dot equals a minus x plus b minus u. A cost, the integral of 1/2 x squared plus u squared. Form g minus as always, 1/2 x squared plus u squared plus p times the quantity a minus x plus b minus x dot. Remember, the Euler equation has two pieces, the partial of g minus a with respect to a variable minus the time derivative of the partial with respect to that variable's rate. Keep your eye on that second piece. Take the state x. The partial with respect to x dot is minus p because x dot is sitting right there in g minus. So the time derivative term is alive and the equation becomes p dot equals minus x minus a minus p. It has a derivative in it. It is a differential equation. Now the control u. Here's the whole point. U dot, the rate of the control, appears nowhere in g minus. So the partial with respect to u dot is 0 and the entire time derivative term vanishes. What's left has no derivative at all. U plus b minus p equals 0. An algebraic equation. You just solve it. U equals minus b minus p at every instant. That is the split, exactly. States and co-states carry their rates into g minus a. So they keep the d by dt term. They are differential, they evolve. The control's rate is absent, so its term dies. Its condition is algebraic, a knob you set instantly. M algebraic conditions, 2 minus differential equations. The skeleton of every optimal control problem. Now let's grind the most important example in all of control, completely. The system. x1 dot equals x2 minus x1. x2 dot equals minus 2x1 minus 3x2 plus the control u. Two states that drift on their own and one control u we choose, pushing on the second. The cost to minimize. the integral of 1/2 times x1 squared plus x2 squared plus u squared. Read it aloud. Keep the state small, that's the x squared terms. But don't spend too much control doing it, that's the u squared. A linear system with a quadratic cost. The linear quadratic regulator, the most important example there is. Here's what it is for a trader, every symbol named. This is optimal execution, working a large order through the day. The state X is your position and the price. The control U is your trade rate, how fast you buy or sell right now, the one thing you actually choose. The x squared terms are risk, holding inventory while the price can move against you. The u squared term is impact, trade too fast and you move the price yourself. Minimize the sum and you've found the optimal schedule. The dynamics are the constraint. So form GA, the 1/2 sum of squares plus P1 times the first equation of motion plus P2 times the second. Two costates, one per equation. Now, let's actually turn the crank. Turning the crank isn't magic, it's just differentiation. So let me show every step. The rule for the costates is this. The time derivative of each costate equals minus the partial of GA with respect to that state. So P1 dot equals minus the partial of GA with respect to x1. Differentiate. Hunt down every place x1 shows up in GA. It's in the cost as x1 squared and inside both dynamics terms. Collect them. The partial with respect to x1 is x1 minus P1 minus 2 P2. Flip the sign and there is the first costate equation. P1 dot star equals minus x1 star plus P1 star plus 2 P2 star. Same for x2. Find it everywhere, differentiate, flip the sign, and out drops P2 dot star equals minus x2 star minus P1 star plus 3 P2 star. We didn't guess these, we differentiated. Now the control. Differentiate GA with respect to u and set it to 0. U sits in the cost as u squared, which gives u, and in the second dynamics term beside P2, which gives P2. So the partial is u plus P2, and setting it to 0 gives u star plus P2 star equals 0. There's no u dot anywhere, so this one is algebraic, exactly as we proved. The optimal control is u star equals minus P2 star, minus the shadow price. Count it up. 2 state equations, 2 costate equations, 1 algebraic law. That 5-line system is optimal execution, fully solved. Let's gather the whole through line into one breath. No matter the boundary conditions, fixed, free, or moving, the Euler equation always holds. When functions are coupled, one vector Euler equation stands for many. When a path can kink, the Weierstrass-Erdmann conditions say a momentum and a Hamiltonian glide through the corner unbroken. And when the path is constrained by a surface, by dynamics, by a budget, you do exactly one thing. Form the augmented integrand GA equals G plus P transpose F and write the Euler equation as if nothing were constrained. The multiplier P that appears is the shadow price, the costate. That single discipline is the whole calculus of variations. And look what we built in the constrained case. A state, a control, a costate, an augmented integrand that is really a Hamiltonian, and a split into algebraic and differential conditions. That is not an analogy for optimal control. It is optimal control seen one chapter early. In the next chapter, that augmented integrand gets its true name, the Hamiltonian, and the rule for choosing the control becomes Pontryagin's minimum principle. At every instant, pick the control that minimizes it. We are finally ready. See you there.